it's finally time to discuss the last main greenhouse gas in the context of wastewater emissions. Nitrous oxide is often overlooked by the public as a greenhouse gas because its sources are lesser known and emissions are less likely to stem from our individual actions. The reality is, however, that nitrous oxide is one of the most harmful greenhouse gases. Another reality: while most carbon emissions in wastewater treatment are indirect, nitrous oxide emissions are entirely Scope 1. In fact, one IWA study from 2019 finds that without active mitigation measures, it is likely that increased nitrous oxide emissions will cancel out or exceed reduced Scope 2 emissions associated with lower electricity usage due to biofuel self-sufficiency on wastewater treatment plants, which we discussed in the last video. This is unsurprising when we consider that the situation has been steadily worsening. Nitrous oxide emissions from wastewater treatment processes have increased by 44% from 1990 to 2014 and are responsible for up to 26% of greenhouse gas emissions of the whole water supply chain, including drinking water supply, wastewater collection and treatment, effluent discharge, and sludge processing. Furthermore, more recent studies find that direct N2O emissions of biological processes in wastewater treatment plants can increase the operational carbon footprint by 78 to 83%. This has resulted in IPCC guidelines being updated to account for nitrous oxide emissions on wastewater plants. One American Geophysical Union report elucidates that nitrous oxide emissions from wastewater treatment in Canada increased by 11% over the past 2 decades, where it was most recently reported in 2017 to be approximately 0.146 megatons per year. Ontario, in particular, had the highest total nitrous oxide emissions from wastewater treatment, dominating 17% of its total provincial emissions in 2012, with an apex of 0.5 megatons. Another study of wastewater treatment facilities in Saskatoon found that nitrous oxide emissions are at an all-time high during the summer months, with approximately 0.042 grams of nitrous oxide per 1,000 liters of wastewater. Again, this might not sound like a lot at all, but let's go back to our Olympic swimming pool example. Treating an Olympic swimming pool's worth of wastewater would emit approximately 100 grams of nitrous oxide into the atmosphere, around the weight of a banana. This sounds like nothing when compared to the baby whale's worth of carbon dioxide emissions from 2 videos ago, but consider the fact that nitrous oxide has a warming potential over 265 times that of carbon dioxide. Even a small amount of it in the atmosphere is undesirable. Essentially, 1 gram of nitrous oxide has the same impact as 265 grams of carbon dioxide. So really, that banana's worth of nitrous oxide is the same as 26.5 kilograms of carbon dioxide, or the weight of a small child. Now, let's learn about where exactly these emissions come from within the wastewater treatment process. The primary source of nitrous oxide comes from nitrification and denitrification processes. Nitrogen-containing wastes like ammonium ions, nitrite ions, and nitrate ions in the final effluent of the activated sludge process can negatively impact the quality of receiving water. These ions are commonly found in human urine and fecal matter, as well as food residue. Major pollution concerns arise, like dissolved oxygen depletion in water and water toxicity, both of which have negative impacts on aquatic ecosystems and human health. 2 specific phenomena can occur: eutrophication and methemoglobinemia. Eutrophication is when there is excess nutrient enrichment in water, specifically nitrogen and phosphorus, which simulates excess growth of algae and other aquatic plants. This is not good, because certain algal species can produce toxins which have detrimental effects on human health and wildlife. Methemoglobinemia is a condition where one has an abnormal increase in methemoglobin levels in their bloodstream, reducing the oxygen-carrying capacity of red blood cells. This can happen when water contaminated with nitrites and nitrates is ingested. So, we definitely need to get rid of these nitrogenous compounds. In recent years, there has been an increase to the attention we pay to nutrient removal in wastewater due to improved knowledge about their negative consequences, which is another factor that may explain the aforementioned increase in nitrous oxide emissions. We do this with 2 processes. First, nitrification is an aerobic biological process that converts ammonia to nitrate. It does this with 2 main types of microbes: ammonia oxidizing bacteria like Nitrosomonas, and nitrite oxidizing bacteria like Nitrobacter. Ammonia oxidizing bacteria do exactly what the name says. They oxidize ammonium ions to nitrite ions. The nitrite oxidizing bacteria then further oxidize nitrite to nitrate. Nitrification typically occurs in the aeration tanks of wastewater treatment plants, where oxygen supplies the growth and activity of these bacteria. During nitrification, nitrous oxide can sometimes be generated as a byproduct, even though it's not present as an intermediate in the main catabolic pathway. This typically happens when there is insufficient aeration in the tank, creating spontaneous anoxic conditions. There's not enough oxygen for nitrifying bacteria to perform nitrification fully, so denitrification occurs to a small degree, which, as we will discuss in a second, can release nitrous oxide in the atmosphere. This phenomenon is called nitrifier denitrification. Wastewater denitrification is used to remove excess nitrite and nitrate from wastewater. It involves the use of nitrite or nitrate ions by denitrifying bacteria, which are facultative anaerobes, meaning they can function both in the presence and absence of oxygen, to degrade carbonaceous biochemical oxygen demand, or CBOD. CBOD refers to the organic carbon present in the wastewater that can be consumed by microorganisms through aerobic or anaerobic respiration, contributing to the demand for dissolved oxygen as an electron acceptor. The denitrifying bacteria utilizes the ions produced in the aeration tank under aerobic conditions during nitrification as electron acceptors for their energy needs, while simultaneously participating in the breakdown of organic carbon, thus contributing to the overall reduction of CBOD in the wastewater treatment process. A more specific name for this process is heterotrophic denitrification. Heterotrophic denitrification occurs whenever an anoxic condition exists, such as denitrification tanks or clarifiers, where oxygen levels are low and suitable conditions are provided for the denitrifying bacteria to thrive. Essentially, the heterotrophic bacteria reduces nitrate to nitrite, which is reduced to nitric oxide, reduced to nitrous oxide, and finally reduced to nitrogen gas, where it can be released into the atmosphere. Did you catch that? While nitrogen gas is perfectly safe to release into the atmosphere, there is a very harmful intermediate compound in there, nitrous oxide. It is only slightly soluble in wastewater and leaves the treatment process as escaping bubbles. So, a question that may arise at this point is, how much of nitrous oxide emissions can we attribute to nitrification, and how much can we attribute to denitrification? Because dissolved nitrous oxide formed during denitrification is mostly stripped to off-gas capture in the aerated zones, the individual contributions from the two processes is difficult to distinguish. However, one 2006 study used enzyme inhibitors to determine that depending on the oxygen levels, 58 to 83% of nitrous oxide emissions are caused by nitrifier denitrification, and the remaining 17 to 42% are caused by heterotrophic denitrification. The question now is this: how can we reduce the nitrous oxide emissions that come from nutrient removal in wastewater treatment processes? There are a couple of optimal conditions for nitrification and denitrification that can help mitigate the amount of nitrous oxide that is produced as a byproduct of these processes. Ensuring that there is sufficient oxygen supply for nitrification to occur in full can minimize nitrifier denitrification. We also need to ensure that there is enough biodegradable organic carbon for denitrification to occur in full, which relates to the CBOD that we mentioned earlier. One 2001 study found that in a bioreactor where the organic carbon to nitrogen ratio was below 3.5, 20 to 30% of the cumulative nitrogen load was emitted as nitrous oxide. Increasing the carbon to nitrogen ratio can help reduce these emissions. Let's quickly discuss one specific potential approach to reducing nitrous oxide emissions in wastewater treatment that is an active and ongoing area of research. As previously mentioned, more nitrous oxide is produced during nitrifier denitrification when there's insufficient dissolved oxygen in the wastewater. Nitrification requires aerobic conditions for optimal performance, while denitrification thrives under anaerobic conditions. These conflicting requirements can lead to incomplete processes and increased nitrous oxide formation. However, a solution being adopted by some wastewater plants is to transition from continuous to intermittent aeration patterns. This provides an interval where dissolved oxygen is lower, promoting complete heterotrophic denitrification and minimizing byproduct formation. When aeration resumes, oxygen is reintroduced, supporting the activity of nitrifying bacteria under aerobic conditions. Optimizing cycle timings to ensure sufficient nitrification and denitrification can help minimize N2O production. Again, more research is required to reach a consensus as to the effectiveness of this approach, but for now it provides hope for the future. Let's wrap up our discussion for today. We've gained valuable insights into the significance of nitrous oxide emissions in wastewater treatment plants, despite their relatively small contributions to overall greenhouse gas emissions. Due to their potent warming potential, These emissions have a substantial impact on the carbon footprint of treatment facilities. We also learned about the essential role of nutrient removal in wastewater treatment, achieved through the biological processes of nitrification and denitrification, which can inadvertently release nitrous oxide into the atmosphere under unfavorable conditions. We also explored factors that can help reduce nitrous oxide emissions and talked a bit about intermittent aeration. Although there are multiple intricacies to the greenhouse gas situation of wastewater treatment, understanding the role that nitrous oxide plays can help us gain a more comprehensive outlook on this situation and take steps towards greater environmental consciousness in this sector.